Welcome back to AI Paper Podcasts, your shortcut to staying ahead in the, well, let's face it, the incredibly fast-moving world of AI research.
It definitely moves fast.
Right. So we know you're busy, you're sifting through tons of information. Our mission here is simple. Boil down the key insights from really impactful papers, give you those aha moments without all the noise.
Get straight to the good stuff.
Exactly. And today we're diving into a paper that feels pretty pivotal. Mixture-of-Recursions, learning dynamic recursive depths for adaptive token-level computation. Bit of a mouthful, so we'll call it MoR.
MoR, much easier.
Yeah, and it tackles this huge challenge. LLMs are amazing, incredibly powerful, but wow, the compute and memory costs are just astronomical, both for training and running them.
It's a massive bottleneck.
Totally. We've kind of been attacking this from two angles, right? Either making models smaller, like parameter sharing, or making them smarter about when they compute that adaptive computation thing.
Trying to be efficient one way or the other.
But what if you could nail both at the same time, effectively? And that's the really ambitious goal MoR goes after.
And that's what makes it so interesting.
Okay, so for everyone listening, if you just have maybe a minute, here's the quick version, the gist of MoR.
The short form edit summary.
Exactly. So basically, the MoR framework is this unified way to get both parameter efficiency and adaptive computation inside one recursive transformer.
How does it do that?
Well, it cleverly reuses a shared stack of layers, cuts down the unique parameters a lot. But the really cool part is these lightweight routers that decide dynamically how much thinking, how much recursion depth each individual token needs.
So not all tokens get the same treatment.
No, so the heavy-duty attention computation, it only focuses on tokens that are still active, still thinking, and it even caches their key-value pairs smartly to save memory.
Okay, that sounds efficient.
Yeah, and they even have this clever KV sharing variant to cut down latency during prefill. The results, honestly, pretty amazing. Across different sizes, 135 million up to 1.7 billion parameters, MoR consistently gets lower validation perplexity, which is good, means it predicts better and improves few-shot accuracy.
And this is compared to standard models.
Compared to standard models, yeah, the same. Training FLOPs, but with smaller model sizes. And it delivers way higher throughput.
Yeah.
So, bottom line, MoR gives us a path to get that large model quality, but without the crushing large model cost. It really could be a game changer for getting powerful AI out there more efficiently.
That's a fantastic summary. And, what's really key here is how MoR fills this gap that's existed for a while. We've seen scaling work wonders.
Right.
Pushing transformers to hundreds of billions of parameters gives us amazing things like few-shot learning, complex reasoning.
Yeah, the capabilities are incredible.
But, like you said, the cost is steep. Memory, compute, it makes training and deployment really tough unless you're, a hyperscale cloud provider.
Right.
MoR hits those pain points head on by combining these two efficiency strategies, parameter saving and adaptive compute that mostly we've chased separately.
It's like they've been on parallel tracks.
Exactly. It's like trying to make a car super fuel efficient and super fast. Usually you optimize for one or the other. MoR tries to do both.
So let's break down those two tracks we were on before MoR. What do they look like?
Okay, so one big one was parameter efficiency. That's basically about, reducing or sharing the actual model weights.
Like layer tying, right? Reusing weights across layers.
Exactly, like layer tying.
Right.
Or, techniques used in things like FSDP, fully sharded data parallel, which helps manage huge models across many machines by sharing parameters smartly. It cuts down the memory needed, makes the model smaller in terms of unique weights.
Okay, so that helps with the size, the memory footprint.
Yeah, but it doesn't inherently change how the model computes things during inference. It might still do the same amount of work for every single token, even the simple ones.
Gotcha. And the other track was adaptive computation, making the model work smarter, not just harder on everything.
Precisely. Things like early exiting. The idea there is that simpler tokens, maybe common words or punctuation, they might not need to go through all, say, 48 layers of a big model.
They can just bail out early?
Kind of, yeah. They bypass the later layers. This can definitely cut down on FLOPs, the actual computational work. But traditionally, this didn't shrink the total number of parameters in the model itself. You still had all the layers, even if some tokens skipped them.
Okay, so one shrinks the parameters, the other tries to shrink the work, but separately.
Right. And the limitation was really finding an architecture that elegantly unified both. Recursive transformers were a step. They inherently share weights, so you get parameter efficiency.
But making them dynamic was the tricky part.
Exactly. People tried dynamic recursion, adapting the compute per token, but it often ran into practical problems, maybe needed complex training setups, or was just hard to deploy efficiently. So a lot of recursive models just used a fixed recursion depth for all tokens. Same number of passes for everything.
Which isn't truly adaptive.
Nope. And that's the gap MoR steps into. It takes the recursive idea, but makes the recursion depth fully dynamic, right down to the individual token level. It connects those two efficiency tracks.
Okay, this is where it gets really interesting. How does MoR actually do this? Let's start with the basics. Recursive transformers versus standard ones. A standard transformer is like a stack of unique layers, each with its own job.
Good way to put it. Each layer has its own weights, its own parameters, unique tools for each step.
And recursive transformers.
They're different. They take a shared set of layers, maybe just a few, and apply them repeatedly recursively.
So instead of 48 unique layers, maybe you have 8 layers that you cycle through 6 times.
Something like that, yeah. That's the core of the parameter efficiency. Way fewer unique parameters. But you can still get a deep, effective network by reusing that shared block. It's like having a versatile multi-tool instead of a whole toolbox of single-use wrenches.
Right, getting more computational depth without needing all those unique parameters. So how does MoR build on that foundation?
MoR layers on 3 key mechanisms. First, obviously, the parameter sharing via recursion. It uses that shared stack. But it's clever about which layers to share.
Oh, it's not just sharing everything.
Well, they tested different strategies, and the best ones seem to be this middle cycle approach. It means the very first layer and the very last layer have their own unique parameters.
Huh, why?
The thinking is maybe the initial processing of the input embeddings and the final projection to output logits. Those steps are kind of special. They benefit from having dedicated parameters. The layers in the middle, though, those are the ones shared and cycled through.
Interesting. So even with heavy sharing, the start and end points matter uniquely. Okay, what's next? The really novel part seems to be the adaptive token-level thinking via routers.
Absolutely. This is the core innovation, I think. MoR uses these small, lightweight router modules. They're trained along with the rest of the model. And their job is to dynamically decide for each individual token how many times it should pass through the shared layer block.
So token by token, like the word "the" might get 1 pass, but photosynthesis might get 4.
Exactly like that. Each token gets a personalized thinking depth. And the huge benefit is that the really expensive part of transformers, the quadratic attention mechanism.
The one whose cost explodes as sequences get longer.
Right. That computation is now focused only on the tokens that are still active at any given recursion depth. If a token like "the" exits after 1 step, it's not included in the attention calculations for steps 2, 3, and 4.
Okay, so it prunes the computation dynamically. It's like an editor sending simple sentences straight through, but giving complex ones multiple review passes.
That's a great analogy. And it dramatically reduces the computational load, especially for longer sequences where many tokens might not need deep processing.
Okay, parameter sharing, adaptive routing. How does this tie into memory, especially those giant key-value caches LLMs need?
Crucial point. Those KV caches store attention memories, so the model doesn't have to recompute them, but yeah, they get enormous, especially during generations.
Yeah.
MoR has smart strategies for this too. The first is recursion-wise KV caching.
Recursion-wise, meaning?
Meaning only the tokens that are actually routed to a specific recursion step store their key value entries at that step. If a token exits early, its KV pair isn't stored for the deeper steps it skips.
I see, so the cache size potentially shrinks at deeper levels.
Exactly. And attention at that step is restricted only to those locally cached active tokens. It saves memory and reduces data movement, the I/O.
Makes sense. And the second strategy, recursive KV sharing.
This one's even more aggressive on the efficiency front. With recursive KV sharing, the key value pairs are calculated and cached only at the very first recursion step.
Only the first one.
Yep, and then those same initial KV pairs are reused across all the subsequent recursion steps for that token, no matter how deep it goes.
Whoa. So you compute KVs once and then just keep pointing back to them?
Essentially, yes. This gives you maximum memory savings and can speed things up a lot because you skip recalculating or even projecting KVs at the deeper shared layers. It's like prepping all your ingredients once at the beginning and just using them as needed for different stages of cooking.
That sounds incredibly efficient memory-wise, but doesn't reusing the exact same KVs potentially hurt performance? Don't they normally evolve layer by layer?
That's the natural concern, right? You'd think the representation should change, but what they found empirically, quite surprisingly, is that this works remarkably well, especially in these parameter-shared recursive models.
Really?
Yeah, the performance drop was often quite small. And they looked into why. They found that the magnitude patterns and the actual vector directions, the cosine similarity of the key and value representations, stayed pretty consistent across the shared depths anyway.
Huh. So the meaning captured in those KVs was stable enough to be reused effectively.
It seems so. It suggests that the core contextual information needed for attention might be established early and doesn't drastically shift across shared recursive steps, which is a fascinating insight itself.
Okay, that's genuinely elegant. Let's dig into those routing strategies a bit more. The paper mentions expert choice and token choice. How do they work differently?
Right, two main ways to do the routing. With expert choice routing, you can think of each recursion step, or maybe a group of steps, as an expert. At each step, a router looks at all the tokens currently active and selects the top best ones to continue to the next step, or expert.
So it actively filters down the tokens as you go deeper, like that strict editor deciding which manuscripts get another round of edits.
Exactly. The number of active tokens likely decreases with depth. The big advantage here is that you get a predictable, static compute budget per step, because you always process K tokens. That makes load balancing across hardware much easier.
Predictable, efficient. But I smell a potential problem. Causality. If the router picks the best tokens, doesn't it need to kind of look ahead in the sequence, breaking the autoregressive flow?
You nailed it. That's the potential pitfall.
Aha!
The router deciding at step T might implicitly use information from tokens later than T to make its choice. They found a workaround, though.
What did they do?
They used an auxiliary loss during training. Think of it like a little side goal that penalizes this information leakage combined with a simple linear router. This combo worked really well, achieving almost perfect separation between the tokens that were selected and those that weren't, and importantly, very few dead tokens that accidentally never got picked to continue.
Okay, clever fix. So what about token choice routing? Sounds different.
It is. With token choice, the decision is made up front. Right at the beginning, each token is assigned a specific, fixed recursion depth it will execute.
Ah, so token X decides I need 3 steps, and token Y decides I only need 1, and that's locked in from the start.
Precisely. It commits to its full thinking path right away. The immediate advantage: no causality violations at all. The decision is made based only on the token itself and its initial context.
Clean. But what's the catch?
The challenge is load imbalance. What if, just by chance, a whole bunch of tokens in a sequence all decide they need, say, 4 steps? Then the expert or hardware handling the 4th step gets overloaded, while the 1-step expert might be idle.
Right, you lose that predictable workload.
Exactly. So the key here was implementing a balancing loss. This encourages the routing decisions to be spread out more evenly across the possible depths, preventing those bottlenecks and making the routing stable and accurate. It significantly reduced the load imbalance, what they called max VO.
Makes sense. So you trade off the causality issue for a potential load balancing issue, but you can mitigate that with the right loss function.
Yeah, the trade-off, yeah.
Yeah.
And connecting back to KV, caching, these routing choices kind of pair naturally with the caching strategies.
Yes.
Well, recursion-wise caching, where you only cache KVs for active tokens at each step, fits really nicely with expert choice routing because the set of active tokens is constantly changing.
Right. You only store what's needed right then.
Whereas recursive sharing, reusing those initial KVs everywhere, that can be particularly beneficial for token choice routing. Since the path is fixed, reusing the initial context consistently makes a lot of sense and gives you that maximum memory saving.
Okay, so the design choices interconnect nicely. This all sounds great theoretically, but, the proof is in the pudding. What did the experiments actually show? How did MoR stack up?
The results are definitely compelling. Across the board, from 135 million up to 1.7 billion parameters, MoR consistently did better than both standard vanilla transformers and simpler recursive ones.
Better how? Lower loss, higher accuracy.
Both. When comparing models trained with the same amount of compute, the same FLOP's budget, MoR models achieved lower validation perplexity, meaning they were better predictors and higher few-shot accuracy.
Okay, equal compute.
But here's the kicker. MoR did this using significantly fewer unique parameters, sometimes up to 50% fewer.
Wow.
Because it's more efficient. For the same compute budget, it can actually process more training tokens because each token might require fewer FLOPs on average due to the adaptive depth. It's just getting more learning done with the same resources.
That's doing more with less. That's exactly what everyone wants in LLM development.
Exactly. And if you flip it around and look at performance with equal data, say, training on the exact same number of tokens, MoR used considerably less compute, around 25% fewer FLOPs.
And that means
Faster training times, they reported about a 19% reduction. And lower peak memory usage during training, about a 25% cut. That's thanks to that filtering effect and the efficient detention on shorter effective sequences. If you're the one paying the cloud bill for training, those are very attractive numbers.
Absolutely. How does it scale, though? Does the advantage keep up as models get really big?
It seems to scale very well. MoR stayed competitive or often outperformed the baselines as the model size and compute budget increased. They noted that while maybe at the very smallest scale, like 135M, vanilla might have a slight edge, that gap closes really fast. For models bigger than about 360M parameters, MoR was matching or beating vanilla performance, especially in low to mid compute regimes.
So it's not just a trick for small models, it holds up.
Definitely holds up, and it really shines when compute is a constraint, which, let's be honest, it usually is.
Okay, training is one thing. What about actually using the model? Inference speed? Throughput that's critical for deployment?
Huge benefit there too. This is where MoR can really shine in practice. They use this technique called continuous depth-wise batching.
Continuous depth-wise batching, what's that?
It's basically a smart way to group tokens together for processing based on how many recursion steps they still need. So tokens that only need one step get processed, then tokens needing 2 steps, and so on. It makes efficient use of the parallel hardware.
Maximizing utilization at each depth.
Right. And the result, they saw up to a 2.06 times speedup in inference throughput compared to vanilla models. The speedup was particularly noticeable for MoR variants with deeper potential recursion, like MoR 4.
Why deeper?
Because with more potential steps, there's more opportunity for tokens to exit early. More early exits mean the average sequence length being processed gets shorter, the KV cache stays smaller, and things just run faster.
So faster inference, lower memory during inference, that's a really compelling package for deployment.
It really is. It makes these powerful models potentially much more practical to run in real-world applications where latency and cost matter a lot.
It really feels like these aren't just incremental improvements. This MoR approach offers concrete ways to build LLMs that are powerful and efficient. It could genuinely help democratize access, letting more people and organizations leverage these large models.
I think so too. And looking at the bigger picture, there are some interesting implications from their scaling experiments. They found MoR models have this distinct compute optimal scaling behavior, meaning they seem to benefit more from adding parameters, making the model bigger, than they do from just being fed tons more data. They seem a bit less data hungry compared to how much they gain from increased size.
So the best way to scale MoR might be bigger models trained for fewer steps.
That's what their findings suggest, yeah. Instead of the maybe traditional approach of smaller models trained for ages on massive data sets, for MoR, the optimal path might be larger, but trained more efficiently for shorter durations. That's a really interesting strategic insight for designing future training runs.
A different scaling recipe. And what about the routing itself? Is it just arbitrary which tokens get more steps, or is there some logic, some meaning behind it?
That's a great question, and they looked into it. It turns out the routing isn't random at all. There's pretty clear evidence that the recursion depth assigned to a token correlates strongly with its semantic importance.
Semantic importance, like how meaningful the word is.
Exactly. Content-heavy words, nouns, key verbs, things like people or drugs, in their examples tended to get routed to deeper recursion steps. They received more processing.
While simpler words,
function words like and, the, of, or punctuation often got much shallower paths, fewer recursion steps. Their role is more structural, less about deep meaning.
Wow. So the model is actually learning to allocate its thinking resources adaptively based on the content itself.
It really seems to be. It's it develops an internal sense of what parts of the input require more careful consideration and focuses its compute there. That's pretty cool.
That is cool. And one last thing they mentioned was test time scaling. What does that mean for someone using a pre-trained MoR model?
This is another really neat deployment feature. Because the depth is dynamic, you can actually influence the generation quality during inference, basically on the fly, by simply allocating more potential recursion steps at test time than maybe it was even trained with. If you need a higher quality answer or generation for a particularly complex prompt, you can essentially tell the model, think harder, by allowing it to recurse deeper for that specific input.
So you can trade off a bit more latency for potentially better results when needed.
Exactly. It gives you this flexible knob at inference time to adjust the model's effort based on the task demands. That's a powerful capability that standard fixed-depth models just don't offer.
Okay, so recapping this whirlwind tour, Mixture-of-Recursions, MoR, looks like a really powerful, unified way to build transformers. It brings together parameter sharing for size efficiency, adaptive token-level computation for work efficiency, and smart KV caching for memory efficiency.
A trifecta of efficiency, really.
Yeah, and the outcome is significantly lower compute and memory costs, often with performance that matches or even beats standard models, plus faster inference. It feels like a very solid step forward.
Agreed. It's elegant, well-motivated, and the results seem to back it up convincingly.
So it leaves us with a big question to ponder, doesn't it? As models keep getting bigger and this ability to dynamically control their thinking depth gets more refined, how might that change how we design AI, especially for tasks needing complex, multi-step reasoning?
Beyond just language, too.
Right. Think about vision or robotics. What new things become possible when models can intelligently decide just how much compute, how much thought to dedicate to each piece of information they process? It feels like a doorway to potentially more sophisticated and adaptable AI.
It certainly opens up intriguing possibilities.
Definitely something to think about. We highly encourage you, our listeners, to check out the paper itself for all the details we couldn't cover. Keep exploring these frontiers in AI efficiency. It's where so much exciting progress is happening.